Welcome everyone to the SDSA student seminar. The student seminar. Today we have our fifth year colleague Anamitra with us. He works with Feloris. How to pronounce his first name? Yorgos Feloris. And today he'll be talking about his work on joint sequential detection and isolation of for dependent data streams. So let's welcome Anamitra.
Hello everyone. Today I'm going to talk about joint sequential detection and isolation for dependent data streams. This is a joint work with my advisor, Professor Georgios Flores, and is supported in part by this NSF grant. So before going into the problem, let me motivate the setup first. So we have multiple data sources that we can call as sensors or channels, and they generate data streams simultaneously in discrete time. And we observe these data, we collect this data sequentially over time, and we have to make real-time decision based on the collector observation at any given time point. There are lots of applications for this kind of setup. In engineering setups, basically, these are very common, like multi-sensor surveillance system, environmental monitoring, power systems. These are very common problems. So in terms of mathematics, let's say we have k data sources that we denote by this red sensors. And at any time point n, let's say from source k, the observation collected is denoted by x and k. So at any time point n, so how do I point this? How do I, yes? Green, or this one? Oh, yes. So yes, so at any time point n, we observe the whole vector xn1 up to xn k, which are k elements. And we have this sequence. So for every sensor, we have this sequence of data, which we called x1, x2 up to xk. So we don't have access to all the sequence of observations here, but at any given time point, this is revealed to us with course of time. Now, okay, so there are some very common problems in this sequential literature. I mean, in like multiple testing literature, where sometimes we are interested to find the anomalous sources. By anomaly, I mean the sources whose marginal distribution deviates from a certain usual standard. So let's say we have, these k many sources. Now each of them is generating data, and some has red, means some are anomaly and some are non-anomalous. So we have to detect these anomalous sources with real time. And so here I'm assuming that the sources are independent. Now, a bit more involved problem, but of the same flavor, is when we have the same anomaly detection problem, but we have dependence between the streams. Okay. So for both the problems, problem 1A and 1B. So for both the problems, how to formulate this problem is we perform multiple testing for all sources, whether the marginal distribution of one source, of every source, follows some standard distribution P versus it follows some anomalous distribution Q. Okay. Now, the second problem is, which is very common in recent times, is how to identify the dependent structure of the sources. So now, instead of doing multiple testing over the marginal distribution of every individual source, what you're going to do is we perform multiple testing for all pairs, whether xi, xj are independent versus xi, xj are not independent. Okay. So we have problem 1, problem 2. So now the natural question that comes is, can we formulate a multiple testing formulation that generalizes the framework of problem 1, problem 2, and beyond? So now, as you, yes.
In the hypothesis testing, can you go back to the,
oh yeah, sure.
One more part of that. So for here, do you have to just know like what Q is for the alternative, or can it just be like not P?
Yeah, that's a good question. So it can be like this, like not P. That is also a possibility. I'm just giving you an example, like just to give you an idea, like what kind of problem there are in the setting of anomaly detection. Okay, but you're right. So it can be a multiple Q, it can be multiple P. Like there are lots of possibilities. Okay.
And all those are in parametric settings. So
no, this can be non-parametric as well. This can
don't make anything.
no. This is just a toy example. Okay, like how things are done.
So what's 1A?
1A is when we have independent streams.
Yes, okay.
When you have independent, so there is no edge, means no dependence. Okay, and this is our dependent streams. Okay, so these problems are tackled in a similar way, but they have some fundamental differences that I'll talk next. All right, so this is the identification of dependent structure with real time. All right, so now we have this question that I posed. Okay, so for both the questions, what we saw is that we are actually performing multiple testing for a subset of sources with real time. So let's say we consider script K to be a finite family of subsets of all sources. So we call these elements as units, their elements as units. And for every unit, let's say XE is the data from sources in E. So for example, if E is IJ, our pair of sources, then XE is XI XJ. Okay. So the interest in both the problems is perform multiple testing for all such unit, whether XE follows some distribution under null, or alternatively, whether it follows some other distribution. So let me illustrate this. Suppose let's say K equals 3. So we have three sources. So in problem 1, we are, if you recall that we are actually, testing the marginal distribution of every source. So that means these are the singletons. And for problem 2, when we were extracting the dependent structure, we are actually testing pairwise dependence. So these units are the pairs. Okay. And we can go beyond this. Let's say we have K equals 2, and we can test for marginal distributions as well as the joint distribution. So this can also be a possibility. All right, so just to give you a mathematical formulation for this problem. So let's say we have so we denote the global distribution P of X, and for every unit E, we call PE. Whenever there is a subscript, there is a superscript, that means we are restricting it to some sources or some subset of sources. So PE means the marginal distribution of X under P restricted to this source E, restricted to subset E. So for every E, we consider two non-empty disjoint families of distribution, which we call HE and GE. And what we want to do is, if P is the true unknown global distribution, that is in hindsight, we want to perform multiple testing, whether P, the marginal of XE, belongs to HE or whether it belongs to GE. And if it is in null, we call it a non-signal. And if it is an alternative class, we call it a signal. And for the sake of theory, let's say P star is the family of global distributions, which is compatible with this problem. Means all the family of global distributions where P, for every unit E, whether either PE is in HE or GE, either it's a non-signal or signal. So is this clear up to this point? Okay. Let's say I illustrated this with a Gaussian example. Let's say we have X is a sequence of IID k-varied Gaussian random vector. So for all global P, suppose I consider that my mean will be in some grid MK, variance will be in VK, and correlation of all the pairwise distribution is in RKJ. Then for the problem 1, let's say if the anomaly is non-zero mean, what we have is HE is when the mean is 0 versus G is when the mean is non-zero. Similarly, for the dependency is correlation because we are in a Gaussian setup. So HE is when the correlation is 0 versus GE is when correlation is non-zero. Okay. So this is what we have for our framework of multiple testing. Now, let's come to the methodology. So a sequential test, now I'll introduce what is a sequential test. So as I told before, so we are observing data in real time. So first I initialize the time point 1. So we sample data from all sources. So we observe the whole vector at time point n. And at any time point n, we decide whether to stop sampling from all sources or we do not stop. So if we stop, then we have to decide null or alternative for each unit. So for each unit, we have to specify whether it's a signal or non-signal. And if not, then we just keep sampling. So this means the algorithm requires two things. One is a stopping time t, which relates to this, and d, a decision rule that relates to this. Now, stopping time is a function of data up to time n at any time point n. So that means it's a function of so t equals n belongs to the sigma algebra of data up to time n, and d is the decision rule that estimates the true signal set. Okay, so after stopping. So now the possible errors that can happen when you put your methodology into action is that, let's say we denote by AP the true set of signals under P. So it's P in GE, means P is the alternative class. Now, as I said before, that D is an estimate of AP, the true signal set. So the possible errors that can happen is false alarm when there is no true signal, but you detect one as such. That means your AP is null set, but you detect something. The D is not equal to null set. Misdetection is just the opposite. So you have some signal, but you did not detect one. You could not detect one. That is also an error. False positive is when you have at least one signal, but also at least one mistakenly isolated signal. So that means D minus AP is not equal to empty set. And false negative is just the opposite, when you have failed to isolate at least one true signal. That means AP minus D is not equal to empty set. All right, so this, I will call this as detection error, and this is called the isolation error. So why? Because this comes from the task of detection, and this comes from the task of isolation. So the main question is, can we have an error metric that controls the detection error and also isolates the signal with accuracy? A possible answer is the classical family-wise error rate control. So family-wise error rate control is driven by isolating the signals. Family-wise error rate 1 means D minus AP is not equal to empty set, and 2 means AP minus D not equal to empty set. So at least one false positive, at least one false negative. Now, the limitation of family-wise error rate is that it controls the false alarm by controlling family-wise error rate 1. So it treats false alarm as a false positive and misdetection as a false negative. Because as you can see that the event of false alarm is belonging to this class, belonging to this set, and also the event of misdetection is belonging in this set. So that means we have a compromise, a possible compromise, that if we want to lower the detection error rate, you have to lower the family-wise error rate, and also vice versa. In terms of mathematics, let's say detection error rates, if we want to put it as alpha and beta, put it below alpha and beta, and family-wise error rate below gamma and delta, then this kind of compromise we have to make. But sometimes it's very crucial to detect the presence of signal. So we do not want to compromise the detection accuracy. But if you have a large number of units, large number of hypotheses, then we want to reduce the stringency to large K. That means we want to relax gamma and delta, means we want to higher gamma and delta, but want to lower alpha and beta. But that cannot be done with this family-wise error rate control. For example, let's say large sensor networks where you have huge sampling cost. You do not want to put more emphasis on isolating the signals, but you want to put emphasis on the detection error rates. So for this, the next question is, now that we have generalized the framework of problem 1, 2, and beyond, can we address these limitations of Hamilton's error rate? So for this is a very natural extension is this proposed class of tests where we control all these errors separately. False alarm below alpha, misdetection below beta, false positive below gamma, false negative below delta. So this is our error metric, and that's why we call it joint detection and isolation. These are for detection, these are for isolation. And alpha, beta, gamma, delta are user specified tolerance level. This can be anything. So these are free, like we have independent treatment for all errors. We don't have any restriction for alpha, beta, gamma, delta. Okay. Next question. Now that we have our error metric, so propose a sequential test that belongs to this class, means that that controls this error metric, also achieve this optimal expected sample size asymptotically, means it achieves the minimum expected sample size over all possible class of test, over all possible tests belonging in this class, means that satisfies the same error metric. And we are saying asymptotically because we want this to achieve when alpha, beta, gamma, delta goes to 0, means when our errors goes to 0. So since we have a joint task of detection and isolation, what we want is the natural thing that comes to our mind is, so we want detection statistics that we call lambda e det n for every unit e. Its large value will imply that there is at least one signal. And an isolation statistics, lambda e iso, such that if it is large, then that will tell me that E is a signal itself. And also we want an online estimate of the signal set, D iso, that will estimate the true signal set AP. So these three components we need to design our proposed test. And the proposed test will look like this. This what we propose in our work. So it has stopping time T star and D star. So stopping time T star is a combination of two stopping times. So it will stop either all the detection statistics goes below are small, goes below certain threshold, or it will stop whether at least one detection statistics goes above, and all the isolation statistics are either large or small. And also at this stopping time, we want the presence of at least one signal. So D iso n is not equals empty set. So now let me illustrate this. So let's say we have A equals A, B equals B, C equals C, and D equals D for every E. So we put this thresholds equal. So then what we have is we reduce to only one detection statistics. So let's say we have K equals 3. That means we have 3 units. Then in the first case, when there is no signal, what you want is the detection statistics to go below some threshold, and that's where we stop. So we stop here. We just see the first type, the detection statistics go below. And in the alternative case, when there is at least one signal, what we want is we want this. So the detection statistics goes above, and the isolation statistics are either large or small. So if it is small, then it's a non-signal. If it is large, it's a signal. So this is how we design our proposed test. Now, I did not tell you how I select the statistics so far. So a natural and practical choice of detection and isolation statistics is to consider the local data from observing from every unit, right? That means lambda E det, lambda E iso. I call it as lambda E, which is the GLS statistics. So the numerator is giving me evidence towards a signal, and the denominator is giving me evidence towards a non-signal. So this is the detection and isolation statistics if we consider only data from the unit itself. As I said, GLS statistics based solely on local data from unity. And this has been done in the literature a lot. But what we figured out is that if the streams are dependent, then detection and isolation statistics based solely on the local data does not lead to asymptotic optimality. Because when a unit is a signal and the streams are dependent, then to declare it as a signal, you want your evidence from other streams as well. So just based on local data will not give you asymptotic optimality. So then the next question is, so how to select the statistics in a more general way that can use data from other streams? So just thinking out of the box, and then can lead to asymptotic optimality. So that's where we come up with the notion of subsystems, that for each unit E, we select two subset of sources, which we call AC as the detection subsystem of unit E, and S prime E as the isolation subsystem of unit E, the same unit. And that will contain the unit E as well. And the smallest choice will be when the unit itself, that will give me the local statistics. And the largest choice is when you consider the whole data, that will give me the all set of sources. So this is the example, this is the illustration that, let's say this is the unit E. We have this AC, we have this S prime E. So to collect evidence, whether it's a signal or non-signal, we are going to use data from all the sources that I am fixing here from the as subsystems. All right. Yes,
So are
please.
you like defining your new unit? So
No. So unit is this. Unit is still
unit is
this.
that pair.
Yes, unit is still this pair.
And
Let's say.
what happens if I just add one more? And what if there exists one unit which corresponds to the added one and the like one of the existing?
I'm sorry, can you?
Let's say the unit that we are considering is 1 and 2.
Yes.
We added this extra 3 to decide
This
the
one?
solution.
3, yes.
Now let's say in the set of the units there was one 3 unit present.
Oh, yes. So for 1, 3, let's say this is 3, okay? So for 1, 3, we select another subsystem like this for 1, 3 only.
No, I'm asking in this example,
Mm-hmm.
do we care about 1, 3 being in the unit or not?
No, we do not care. We do not care. 1, 3 may not be a unit as well. So it's just for this. This is just for one example, that for this unit, we are also considering. So these two subsystem can be equal. I'm just doing it different for generality. Okay. So now that we have our subsystems, so now I will compute my detection statistics based on my detection subsystem. How do I do this? I'm not going into mathematical details. So basically what I'm going to do is, I'm again computing a GLS statistics. Now the numerator is going to give me evidence towards whether E is a signal, versus the denominator is going to give me the evidence whether there is no signal present. Okay. So that means if this likelihood ratio has larger value, that means we have stronger evidence whether there is at least one signal. Similarly, for isolation statistics, in the numerator, we have the evidence towards whether E is a signal, versus in the denominator, we have evidence towards whether E is a non-signal. That means if it is large, then we have a stronger evidence that E is a signal itself. So this is how we generalize the idea of local statistics, by considering data from other sources. And the online estimate of the signal set is all the units which has isolation statistics bigger than 1, which has larger isolation statistics. I will call them as my true signal set. Question?
Yeah.
Yes.
So I'm a little confused about the
Yes.
definition of the P star. So P star is like joint on all the nodes, right?
No, P star is all the probability measures that are compatible with this problem. Here. Oh, sorry. Yeah. Either it's a signal or non-signal.
Oh, so based on these distribution on units, you build your P star.
Yes, I build my P star. So for HE and GE, So H and G are specified to you by the practitioner, whether it's a mean zero or mean non-zero. Based on this, I create my P star, all the family of global distributions, which is compatible with this problem. Okay. Any other question? Yes.
Maybe you'll cover this later, but you talked about the subsystems, right? Like
Yes.
you have to choose. So it seems to me like there could be multiple subsystems.
Yes, exactly.
that
You are right.
satisfy this criteria.
Exactly. That I'll talk later. That's a very good question. So there are multiple choice of subsystems. The smallest choice is this, the unit itself, that has been done so far in the literature, and that's what we call the local statistics. You just compute your statistics based on the local data. Okay.
That you're saying doesn't give the asymptotic.
Exactly. So that was done in the previous literature, and that could not give me asymptotic optimality. There are multiple possible ways you can choose your subsystem. This is just one example. The largest choice is when you put all the data for carrying evidence for every unit. Okay. All right. So detection statistics and isolation statistics I created based on my subsystems. Now error control, as I told previously, that your T star D star has to be like the proposed test has to be in this class that controls the errors alpha beta gamma, below alpha beta gamma delta. So how do I choose my thresholds A, B, C, and D? That is done by this theorem. As you can see that A and B are controlled by these isolation errors delta and gamma. C and D are detection statistics, detection thresholds that are controlled by these detection errors alpha and beta. So very nice. We have our 4 thresholds that are controlled by the 4 specification of the error control. All right, and for the asymptotic optimality theory, I'm just assuming that based on this theorem, I'm just going to choose my A, B, these thresholds as like this, which scales with these parameters alpha, beta, gamma, delta. That's not so important. All right, for the asymptotic optimality theory that I just mentioned, we need some distributional assumption. I'm not going into detail, but what we want to assume is that for every P in the null class and for every Q for every P in the alternative class and for every Q in the null class, there are these numbers, information numbers that you can interpret based on only on the data, based on data only from subsystem S, such that this kind of some notion of law of large number holds. So your scaled log likelihood ratio goes to this number. So for IID sequence, we have strong law of large number, and these are the Kullback-Leibler divergence number. And for non-IID sequences, we have like for autoregressive models and state space models, this kind of assumptions hold. All right. So for optimality results, let's say we have this information numbers. This is giving me distance between 2 distributions, P and Q. Now we have fixed up distribution P and some class of distributions Q. So I defined another measure of distance between this P and this class Q based on sources in S, which is this. So the first optimality result tells you that if this condition is satisfied, if you choose your detection subsystems, coming to your question. So if you choose your detection subsystem like this, so there are many possible ways you can choose your detection subsystem. If you choose your detection subsystem like this, then you have your optimality when there is no signal. Okay, and this can happen when AC equals K, means you choose all the data for every unit E as your detection subsystem. Now the same kind of conditions are there when it is in a null class. This is a null class, and this is the optimal performance that is achieved by our rule. So just to give you an idea, not going into much theoretical details. So this is the difficulty of the problem. This here is the difficulty of the problem that is appearing in my optimality results. That is known by an oracle, by a god. And this is what you want to achieve by choosing our subsystems. To, if we match our knowledge with the knowledge of an oracle, that's where we achieve this optimality. And we have this takeaway that at least when I choose my detection and isolation subsystem to be the whole set of sources, the all sources, then we can match this. Then we can match these numbers. Yes.
So when like you were like trying to satisfy all the conditions that you have written, like 2, 3, 4.
Yes.
So in all the conditions, you have always mentioning that if your subsystems are the whole set,
Yes.
you will satisfy.
Yes.
So what is the actual problem if we like always select the subsystems and the whole source? So we will that be like too much
yes.
time consuming?
Exactly. So this is my second part of the. So this is the takeaway from the theory. If we choose subsystems as the whole set, we have optimality. Okay. So with this takeaway, I apply this in case of independent streams, the problem 1. So you have independent streams, that means we have multiplicative distribution. And if we choose all the data from all sources, what we have is we have a very nice form. We have a very nice form of T star and D star. I did not mention D star here. So T star is a very nice form, and it is also computationally very efficient because it only needs ordering the local statistics. Okay. And the best thing is this matches with the existing result in the literature. That means what we generalized in our theory that explains the literature that was done in the past, and that validates our theory. Okay. Now I go to application 2, which is the next problem, which is the extraction of dependent structure. Then setting this suffers computational complexity because it takes too much time, and also it requires you to compute so many likelihood ratio statistics. So when the streams are dependent, there is a computational complexity issue that you just mentioned. So then the next question is, can we propose a practical test that enjoys this lower order computational complexity and also achieves optimality under large class of distribution? The most natural thing that come to your mind is with the smallest subsystem. Choose the smallest subsystem. Let's say we have AC equals S prime E equals E. So we use the local data that was done in the previous literature. So, and by the definition of this detection isolation statistics, they both reduces to this local statistics lambda E, and we have the lower order complexity rule, which is this. See, even you just only need to find the maximum of the minimum of the likelihood ratios of the local statistics. Now we become more greedy. That can this practical rule also achieve optimality under at least some setting? The answer is yes. So following 1, 2, 3, 4 that I mentioned here, these bad looking conditions here, so I knew that when AC equals whole set, we have this equality. But coming back to your question, but when AC and AC prime are not chosen as this, there is still a possibility that these are equal. Okay. So this is where I said that following these conditions, if the signal setting is like this, then we can achieve optimality even with the practical rule. So the conditions are, if the most difficult to isolate signal is independent of the rest, and the most difficult not to isolate non-signal is independent of the rest. So the most difficult to isolate signal means, let's say we have this k many sources, and this is yeah, so this is a signal which is very, very low in its strength and which is also independent from the rest. So this is what we call is the most difficult to isolate signal. And also there is a non-signal, which means there is a independent pair of sources which is also independent of the rest. So under this sparse signal setting, we still have our practical rule to achieve asymptotic optimality. So this is the most interesting part of this project, that even though you do not have your access to all the data, you can still achieve asymptotic optimality under dependent streams setup. So let me illustrate this with a simulation study. Suppose for this is a very small scale simulation study. That's just to give you an idea. So let's say we have 7 sources, Gaussian distribution, mean 0, variance 1. The true covariance matrix is like this. So we have one independent non-signal. This is this one independent non-signal. This is one independent signal. Okay. In this case, we know that practical test is asymptotically optimal. And this is what we have in our simulation study. So we have my subsystem of size 2, which is the which uses the local data. That means which is the practical rule. And even if we increase our subsystem of size 3 to subsystem of size 3, they are very similar in their performance. So this is the expected sample size of the tests, and this is the error. Yes, the log of errors. And as you can see that from the takeaway from the simulation study is, even if you increase your subsystems, there is not much improvement in the performance of the tests because they are both asymptotically optimal. And yeah, that's it. I think I'll summarize this. So we generalized the framework of multiple testing for dependent test streams, and we formulated a novel error metric, which is called joint sequential and detection and isolation. We proposed a family of tests that allows diverse computational complexity as well as enjoys asymptotic optimality. So these computational complexity issues are coming from how you choose your subsystems. There are many possible ways to choose the subsystems. If you have the lowest subsystem, that is the practical rule. If you have the largest one, you'll have asymptotic optimality, but not practical rule. So we propose practical tests also for lower computational complexity. And I showed you that this is asymptotically optimal under a large class of distributions. And then we applied the tests and the theories to the traditional problem of this kind of problems, this identification of anomaly, extraction of dependent structure, and all. And these are references, and thank you. Yes, please.
I have 2 questions.
Mm-hmm.
The first one is, do you think it is possible to quantify the relationship between the subsystem size and the asymptotic efficiency under a general setting?
So that's a good question. So quantify means you want to see how bad are we doing, like this, like how
because we know
much.
That if the subsystem size is of the same size as the whole network,
Yes,
then it is asymptotically. It is always
asymptotically optimal. Yes.
Yeah, but if it is only the unit itself, then it is not asymptotically optimal. So
Not always.
Yeah. So I want to see under a general setting, if we increase the subsystem size, do we have a, supposedly the asymptotic efficiency will improve.
Yes.
So can we see that improvement?
So can we, so if we achieve asymptotic optimality with the smallest subsystem, that means we achieve optimality with every possible subsystem. Does that make sense? So because if you see here, if you see these conditions here, so if I plug S prime E and AC as my smallest one, and if it the equality holds, all the bigger subsystems that is bigger than the bigger than the unit, the E, then that will lie in between. So there is a monotonic relation between this. So the larger AC or S prime E closer to this value. Okay, so if it is achieved by the smallest one, that means all in between will achieve the same one.
So you mean the dependent structure decide the optimal subsystem size?
I'm sorry, can you repeat?
The dependent structure of the unit
Yes.
decide the optimal subsystem size.
Yes.
So if we suppose I have a pilot sample that I can estimate the dependent structure.
Yes, that's a very good point. So that's the future research, that how to choose these subsystems, SE and S prime E efficiently, that can lead you to asymptotic optimality very fast.
Okay.
So
my second question is related to the theorem where you control the fault error rate.
Oh yeah, sure.
So I'm not very familiar with this competition. So what I know is that in the usual setting of hypothesis testing, we can only control type 1 error or type 2 error at one time. In false discovery rate, we also choose to control another type of error rate. So I want to ask, how is it possible?
Oh yes, in sequential test, you can control all kinds of error rates simultaneously.
Yeah. Can you give an intuition why this is possible?
And also,
the C is not like basically that C isn't empty.
C is
Like that C, like how do you know there's a test that will satisfy those things? I think because we're always like in classical statistics taught like trade-off between type 1 and type 2.
Yes.
You're not going to have a test that can make both of those go to zero.
No, in fixed sample size setting, right?
Yeah.
But what I'm having here is not fixed sample size. Our sample size is not fixed in advanced.
For some power and for some.
Yeah, so here I can control all of them together. And also, as you can see, that these thresholds do not depend on the probability measures. They only depend on this delta and beta and the number of the class, the cardinality of the class, but does not depend on the true probability distribution.
Thank you.
What was your answer though, that sample size solves it all though? You're saying that for some desired type 1 and type 2 error pair, that there's some sample size that's going to, you basically, you can take the sample large enough to satisfy that desired pair.
So when you
that seemed to be your answer to AMR.
No, so when you want to for fixed sample size setting, let's say when you want to control type 1 and type 2 error both, like put type 1 error and power, what you do is you want to find this optimal sample size n such that this both happens, right? But here, when you want to use this likelihood ratio approaches, like this likelihood ratio approaches, it doesn't suffice to do that. It doesn't, it won't be necessary to do that.
Oh, okay, not necessary.
Yes.
So can you please go back to the image where you had
Subsystems?
Yeah, the last one.
Oh yeah, sure. Oh yeah, this one.
Yes.
Mm-hmm.
So in this one, are you assuming that the signal is only present in the pair that you have represented there?
Yeah, signal means dependence here. So I am in the problem 2 setting. Okay, so extraction of dependence structure.
Right.
So dependence is a signal.
Significant only for that. Is that what you were
Yes.
saying?
So dependence. So that means, so we have a cluster of sources which are dependent among themselves. There is a pair of a dependent pair which is independent of this cluster, and the signal strength is very low.
The smallest.
Yes. So that's the signal strength is low, means that is the most difficult to isolate, and independent of the rest means this is independent. This does not involve in the main dependent structure.
But while recovering these signals, you do recover
Oh yeah, for sure. I do recover all of them.
So that's what we mean by optimality.
Yes, yes. Yes. Yes, please.
These two conditions for.
Yes, sorry, Tommy, this would be the last question you're.
No, I still have 11 minutes, right?
It's probably a fast question.
No, I mean, that's just Tommy would be the last.
Yeah, please.
All right.
Yeah.
Quick question about this. When it comes to like real data, how reasonable do you think these two conditions are?
Oh, that's a very good question. So, when in real life, so if you remember the application setting that I mentioned there, here in real life, what we have this wireless networks, large power systems. What we have is like we have a large network of sources, and some like the signal is present in a very small number of sources actually. Okay, and we have to, and the most of them are like independent. So that's where.
Wait, very small number of sources, as in like 3 or like.
No, let's say we have k equals 100. Let's say k equals 100. The total number of sources, let's say 100, and we have a large cluster of sources which are dependent among themselves, and it is possible that there are like very few sources which are like detached from the actual dependent structure, but the signal is very low. So this is very natural setting. This is very natural possibility, in this kind of application setups. Like in gene structure as well. Like in so when you have a sparse covariance matrix,
Okay.
so you have this you have a large covariance matrix here, and most of them are 0. So that means dependence. And you have a very few genes which are correlated to each other, and very I would say low strength genes. Okay, so this is a very common scenario that can happen in dependent structure.
Thank you, Anamitra.
Sure.
Lunch is in the common room.